The next of the common circuit structures we're going to look at involve two resistances, R1 and R2, in parallel with a power supply, either a voltage source or a current source. When two resistances are connected in parallel, you have two different paths for the source current to split into. The source current comes into this node or point of connection, and some of the current goes this way, and some of the current continues on and goes that way. And it can be shown, and it should be intuitively obvious, that the sum of these currents, I1 plus I2, must equal the total current I sub s, or I sub s equals I1 plus I2. You can think of this in maybe in a little more common terms. If you've got, say, 5 gallons a minute of water flowing into a T in a piping system, if you've got 5 gallons in, you're going to have a total of 5 gallons going out. If 3 gallons come this way, you're going to have 2 gallons going that way. In a similar sense, current is a rate, only instead of gallons per minute, we're talking about coulombs per second or amperes. But if we have 5 amps coming in, we have 3 amps going this way, the other 2 amps must be going that way. It can be shown, and we won't do it in this class, but in a later class we'll derive that the total resistance, the equivalent resistance seen by this source looking into these two parallel connected resistances, can be determined by taking the product of the two, R1 times R2, divided by the sum of the two resistances, R1 plus R2. For example, if we let R1 equal 10 kiloohms and R2 be 1 kiloohm, the parallel equivalent, or the total resistance seen by the source pushing at them, will be R1 10K times 1K divided by 10K plus 1K. And that gives us 10 divided by 11, or 0.909 kiloohms, which is equal to 909 ohms. One thing you'll notice is that the equivalent resistance, the resistance that this source is pushing against, is 909 ohms, which is less than either of these two resistances. And you might say, how can we combine resistances and in the process end up with a lower resistance? Well, in fact, if you think about it, if with only one path, if this path wasn't here, you'd have 10 kiloohms of resistance. Similarly, if this resistor was in place, the 1 kiloohm resistance was in place, but not the 10 kiloohm resistance, you'd have one path with 1 kiloohm. If you then open up two paths, even though the resistance here is 10 times as large as this resistance, you'll still have more current flowing through two paths than you would have had through either of those. So more current flowing suggests less resistance, and in fact that's what we see. The parallel combination of two resistors is less than the smallest of the two resistors. Now there's an analogous concept of current division, analogous to what we saw with voltage division. In voltage division, the two resistances needed to be in series with each other. Here in current division, as we've already seen, when two resistors are in parallel with each other, the current coming into the node or the connection is divided between the two resistances. And it can be shown that the current I1, the current going through R1, is equal to I sub s times R2 over R1 plus R2. And similarly, the current going through I2 is equal to R1 divided by R1 plus R2. The thing that should jump out to you immediately that's different, well, first of all, we have a similar type of ratio as we had in the voltage division circuit. We had one resistor divided by the sum of the two resistances. Now the thing that should jump out at you, or another thing that should jump out at you, is that the current I1, the current through through R1, is proportional to R2, the other resistor. And similarly, I2, the current through I2, is proportional to R1, the other resistor. How does that make sense? What that's saying is that I1, this current here, gets bigger as R2 gets bigger. Now as R2 gets larger, less current is going to be allowed through this resistor. It actually restricts the current here. So any less current that's going through here must then be forced through this one. Thus I1 gets bigger as R2 gets bigger. And similarly, I2 gets bigger as R1 gets bigger for the same kind of reasoning. Now let's go ahead and show how these current divider formulas can be used to determine the current through I1 and the current I1 and I2. Let's let I sub s equal 11 milliamps, and we'll use these two resistances here. Thus, using current division, we can say then that I1, the current through R1, will equal I sub s, which is 11 milliamps, times R2, which is 1 kilo ohm, divided by 10 plus 1. Now we don't typically write the units when we're doing calculations, so let me just kind of erase that or scratch that out. Anyway, we have then the current going through R1 is going to equal 11 times 1 over 11. 11 times 1 over 11. Or 1/11 of the current is going to go through here, which is equal to 1 milliamp. And similarly, I2 is going to equal 11 times 1, or times, I'm sorry, 10. I2 is going to be I source 11 milliamps times R1, the 10 kilo ohm resistor, over 10 plus 1. And that equals 11 times 10 11ths, or 10 milliamps. And once again, you'll notice that the total current, I1 plus I2, is 1 milliamp plus 10 milliamps is the 11 milliamps. So we have a resistance here, R1, is 10 times as big as R2. And notice that the current going through R2 then is 10 times as big as the current going through R1.